Thank you. Well, thank you for having me. And just adding one more stop before, well, during and the whole throughout my PhD is also I spent some time in Tübingen, Max Planck Institute. So there's also some collaboration for the things that I'm going to talk about. And yeah, just a disclaimer, it's probably not the most recent. I will start from all the journey of the past 5 years of that led to the final things. But before that, I want to do this tiny advertisement that is not that far. If you happen to be in Paris, 4 hours by train, come visit us. Where we have this computer vision team called Imagine with 6, 7 permanent researchers and the students around them all together. There's some pictures from our Christmas lunch or lab retreat or CV t-shirts. But yeah, so I'd like to start with the umbrella of the things I'm doing can be grouped into vision and language, but I'll focus on one of them today. But I wanted to still show like one sneak peek of each of the things, well, more like computer vision tasks I'm doing. So it could be this vision and language where vision is dynamic visual data typically. So it can be mostly videos, but I do like 3D human motion as a form of, it's arguable whether it's visual data, but it's some form of dynamic data for sure. And in the video understanding part, we do a lot of text. For example, that's the one with sound. So I'll just turn it on, but there will be subtitles anyway. So we're trying to do a movie description. So this is like intended for a blind audience to follow the story. So it's a bit different than captioning some video. You want to have like character-centric, story-centric captions. And the state of the art and the state of the research at this moment looks like this for friends.
Isn't that amazing? Joey and Chandler watch TV together.
So that's our prediction. And then the graphic.
Rachel looks at a piece of paper.
Okay, they hug each other. It looks at a paper. So it's still quite grounded visually, not necessarily following the story. So that's the current challenge, is how to link it in a 1 hour video to make it coherent. But the visual aspect, so getting the visual objects from video to text, that part is getting better and better with the large models. Another example is video retrieval. So you want to search, type some text and like not generate, but retrieve from existing videos the top ranked one. So I will show a demo of a work we've done in 2021. It's getting better now. So family, search for all the videos that have related. Family camping in the snow, family camping in the snow at night. So the nice thing here is compositionality, right? Like good old days action recognition, you had one word or one class that is associated to each video. And realistically, there's lots of things going on. So thanks to these like clip-like models, text and video embedding space that are in common, we can do these things a bit more fine-grained these days. And one part of me that spends a lot of time on particular types of videos is sign language for the ultimate goal of translation. So you have, again, it's like captioning, right? So video in, text out. But to get there, there's no data. So we have to do a lot of automatic annotation to get like word sign correspondences. So we partner with BBC to get interpreted data for this. And for the first time in the last few months, we've got something that's reasonable, not embarrassing, to be able to like show qualitative results. But so far, since like, 2019, nothing really was working. So that's like, anybody who's looking for a problem which is unsolved, it's there. And the one I'm going to talk about is about, again, language. So it's with text, you have put hands on the waist, move torso left. You want to generate a few second clip of 3D parametric body model in motion. So there's no video in here. Well, there could be, but so that's more like text to human motion generation. You could think of the other way around. Motion to text would be motion captioning. There are less works for that. But yeah, I'll talk about that one first. And to motivate that, let's look at this Spider-Man movie clip for a few seconds. It's crazy. I don't know if the lighting, yeah. All right, so this awesome scene, how was it created? So there could be some part of that motion in this static scene with motion capture markers, like motion capture suit, multi-view cameras, some stage for doing some acrobacy. And some of the motions, they need like even more special equipment. In indoor scene, they capture this part and they put them together. And some parts are not even physically plausible. They can, like this one, it's like flying in the air. It's not even capturable in that sense. You can go and manually click, and animators can make them move this way, and it can take hours and hours. So the question here is, can we generate human motion to make part of this process a bit more cheaper and faster? And we know that text-to-image generation, you can type some text, like a family having a picnic, and have pretty like high fidelity image generations. What we want is something similar, except that the text is quite specific. A person is walking forward, raising both arms in the air, and then jumping. And we want to have like this sequence of motions. Any questions so far? Good. Then I'd like to just say a few words on why we're doing generative motions beyond all these applications to motivate. I recommend this book, which came out a couple years ago, that has all these interviews with well, key people in AI these days, so you get to see some of the background stories of what's happened. That quotes from Joscha Bengio and Goodfellow that refers back to Feynman's code. What I cannot create, I do not understand. And it's a bit similar. What artificial intelligence cannot create, cannot understand. So the discriminative models that can find shortcuts, probably like action recognition, picks up on some, I don't know, like if it's a specific dance action, and maybe you need to wear some clothes, so there's like spurious correlation. It picks up on the clothes to recognize that dance. But if you need to generate, you have to generate the whole complexity of that movement as well. So the idea is to better understand. So first, I'd like to do a little raise of hands to understand the audience expectations, to say whether this video is a real or fake motion. Who thinks it's fake? Who thinks it's real? Who is not paying attention? Okay, it was half and half. I would say it's real. It's an Australian Olympic artistic swimmer that came to Paris. You can watch her forever. It's amazing. And this one, who thinks it's fake? Right. I mean, we are very sensitive about like human faces and bodies in general. If something is wrong, we can tell quickly. So this is the state-of-the-art Sora from OpenAI video generation. So just to say that human motion is complex to generate, right? So we're not doing that. We're not doing the video. So I'll show more the 3D motions, but you can imagine those to be applied to videos later. And what we've done so far in this direction, I can summarize in one slide. And I'll not go into detail of each of these, but just to show you like sequence of how things evolved. We've started with what we call action condition synthesis. So you have a given input, a category, and you want to generate randomly some sequence that follows that. And then we went to like open vocabulary, free-form text condition. So human walking in a circle clockwise, you want to generate the motion. So that's the base of most of the follow-up works. So just showing you input-output relationships here to define the task. Temporal compositionality is for sequence of action, so one after the other. You have hold golf club, swing golf club, see if it's playing, jog forward and kneel down. So this is the temporal smoothness aspect we're looking at. The one after is spatial compositionality, so the name is just to have an analogy, but it means simultaneous action. So doing two things at the same time. It's the put hands on the waist and move towards the right example we've looked at. And you can say, okay, isn't there something more general that encapsulates both spatial and temporal? So that's what we call multi-track timeline. So you can have walking forward up to this point, start raising hands in the air, and at this point start jumping. So it's like a bit more easier interface for, let's say, an animator to use. And also method-wise, it's much easier to make that work. And slightly different one we have looked at is motion retrieval. So a bit like text-to-video retrieval, but you type some text, human walks up the stairs, and you want to retrieve existing motion, so you don't generate. Maybe you have enough motion capture data already, you just want to search, maybe you want to automatically annotate them, so that could be several use cases. There's a demo, so you can try these things also on your own. And the last one, which is the most recent one I'm quite excited about, is editing. So you have a red motion, which is the source, and a text kick higher, and you want to generate, let's play it again, the green one. Get the idea. So there's a bit more like towards fine-grained generations, but also we know that if you have this text to even image generation models, you type something and you have something in mind, it doesn't give you that thing. So you just randomly keep generating the next one. Instead of that, you could iterate. So you could say, generate me a kick, and then say kick higher. Now put your hands in here. So it could be easier for a model to digest rather than like this giant sentence that says them all at the same time. Okay, so any questions so far? Then we'll go slightly more in detail in some of these. The first one is kind of the base of, in terms of the neural network architecture we built for this, it's still used today quite widely, is the action categorical one. So you have predefined set of actions and you pick one. And how to get data was like the first question for this, because there's nobody labeled semantically motion capture. There's lots of motion capture, but they just say it's a dance, but it's not like a spin or put your hands on the floor. There's no real action units. And there's a lot of that for video, for some of the Kinect or 3D action recognition data sets. It's just that the skeletons were typically very noisy, and we've estimated them from some monocular 3D pose estimation methods, for example. At this point, it was live in 2019, the state of the art. Now it's much better. But just a little parenthesis here on how to even model 3D human motion. Well, let's forget about even motion, but just the pose. And actually, like Hinton's first paper, because it's a very important problem, was focusing on human pose. And there, back in the day, people were looking at skeletons, 2D pictorial structures with like rectangles. And then people also tried like 3D geometric primitives to approximate body with spheres or cylinders. But now we have slightly more expressive and controllable models. One of them, like widely used, although being already 10 years old, is simple, SNPL, which is a parametric model given pose, like low dimensional representation, like 72-dimensional, for example, pose, and shape parameters, which is a PCA space of the variation of identity. So how fat or how tall or like this identity-specific deformations. Versus the pose is the articulation, so the rotations between joints in the kinematic tree. So given those, the simple model is a linear function, basically, that converts them into vertices. So the coordinates of the mesh points, the vertices on the mesh. And given those, you can also regress the joints if you really want to get the skeleton. But that's kind of the very high-level idea of the model. And we use that representation frame by frame, sometimes like get some extra features like velocity on top, but that's the basis of the representation. And given those, our goal is basically action conditioned, right? So we have this pickup, which is normally one hot vector encoding if I have a closed vocabulary, and the motion. Well, we designed a variational decoder, VAE. That's why we have an encoder and a decoder. The goal is to give the motion reconstructed again. So we give it at the input and the output. And the condition, the action, the one-hot vector encoding A is given also both to the encoder and decoder. So that's the general idea of a conditional VAE. At test time, you discard the decoder so that the input becomes a random sample from a Gaussian distribution and the action you decode. So the difference here, I'll show the internal of the model, is that we also specify how long the motion should be at test time. During training, it could be the ground truth duration. At test time, this is one of the sources of variation as well. And internally, the encoder, well, here it's like some transformer model. That was the beginning of those models. And we show that it's better than these recurrent ones. It's better than autoregressive transformer decoders to generate the whole thing at once. So I guess the encoder is relatively straightforward. Well, one thing I should mention is to make this transformer a VAE, you need those two components, right? So the mu and the sigma, the mean and the variance of the Gaussian distribution. And transformers are quite flexible in terms of the sequence length that you input. We just add 2 learnable tokens to the beginning of the sequence and get the corresponding output as if they are the distribution parameters when we obtain the Z from the 3 parameterization. What's interesting is on the decoder side, we give the queries as the positional embeddings as many times as we want, as long as we want the sequence, we give as many positional encodings. So that given a single motion representation, Z, it's in like 256 dimensional, I don't remember, vector, you can generate the whole motion at once. And then there's the reconstruction loss on the vertices, on the joints and the rotations, all that ablations in the paper. Any questions on this figure?
What happens if you do it autoregressively?
What happens?
If you do it autoregressively?
We did that. So that was the first thing we did. And then it was very interesting because there was this wave or some salute or some of the action which was supposed to be waving. And then we encode the ground truth motion, which the model has seen during training. And we decode it. It waves with the other one with left hand, and you encode with left, and then it decodes with right. Because initially, like it always starts from some rest pose, and then it frame by frame generates the next. And probably like this Gaussian distribution, they were all like generating the similar motions. So it wasn't really paying attention to the entire motion in a single vector. So it was, I mean, already it is doing that for the encoding, but for decoding, it was drifting. So that was one issue. It was also a bit jittery, and performance was worse. So then so it was the same as the GRU, like some recurrent neural network. I'll show some of the results of the GRU, but I don't have the transformer one, I think. I just have numbers. I remember we were so frustrated why this doesn't work.
I have one question from this slide. So I understand that the VAE part comes from the mu and sigma and the reparameterization.
Yes.
I don't understand the mu token and sigma token for the action. So how does that come?
Well, it could come anywhere, but we chose it to like there are some linear layers here. So this is one hot vector encoding to make it specific to each action. So imagine it as multiple Gaussians. Let's say I have 12 action categories. I would have 12 Gaussians that are a little bit. So we also chose this to be additive. So we tried a few things, concatenating and stuff, but this was slightly better to wire things this way. But you're familiar with like CLS token and transformers in BERT or CLIP. So it's a bit the similar idea. We just have 2 tokens instead of 1, which is learnable, but it's conditioned on the action. For each action, you have another one. So it's in practice, it's a lookup embedding as many as actions. Yeah. Any other questions? Well, the code of this is pretty nicely written. So if you are interested, it's understandable. So some qualitative results: pick up, high knees running, punching and knee lifting, left stretching. Even if we see some text there, it's just some categorical IDs. In terms of diversity, so this is side kick with different random samples. It could be left or right. hands are irrelevant, so there could be anywhere. So that's basically what we want to achieve, so to get the irrelevant parts as random as possible, capture all the variants, but it depends on the data. And one nice outcome was, remember the ground truth comes from videos to 3D estimation, so they are quite noisy. What we do here is if we encode that motion and decode it back from our model, it gets smoothed. So that was like a side product of denoising. We thought we could even improve motion estimation from videos, which didn't have the energy to compare with all the benchmarks, but I think you could just plug it in. Okay, so that was action categories. From now on, it's going to be a bit faster because everything builds on that. We want to move to free-form text, not just have these 40 categories or 20 categories. So the input should be a human walking in a circle clockwise rather than just walk. But even then, because language by definition has ambiguity, there is like degrees of freedom that remain. So what's the size of the circle, shape of the circle? So we want to have variation on that while having fidelity. And the model itself is quite similar in terms of the internal architecture. It's a transformer and stuff. But we take inspiration from the previous work at the time called Language to Pose that has this, to integrate text encoding, it has this 2 branches. So there's a motion to motion VAE, the same as before, except there's no action conditioning anymore. There's just mu and sigma there. And then there's the text to motion branch, which is the one we want to use at test time. It's not a real conditional VAE anymore. But the objective is you want to put alternate between these 2 branches to put the reconstruction loss so that it can generate, the decoder can generate realistic motions. So that's the job of the motion encoder part. And it should follow the text. So that's the job of the text encoder part. So it alternates between the 2 embeddings. But there's an additional loss to make these 2 similar to each other. Just like minus, these 2 should have close to, the difference should be close to 0. And that's pretty much it. And the text encoder, you can take existing language encoders, the better it gets, the better here. But we just chose something simple back then, Distilbert. The difference from prior works is really to make this probabilistic, because all the other works, they were doing text to motion as if it's a deterministic problem. Only one motion. And the data now we have, well, there's the kid motion language data set. At the time was one of the 2. That has annotated, so types text for 4,000 motions that are clean motion capture motions. And the text, even if they are free form, they are not really that much compositional, except like there could be left hand, right hand, human walks in a circle. That's a lot of locomotion, how they walk, but not as much diversity in their actions. But it's good enough to train these models, at least, to get some source of diversity, at least like for like person jumps forward for the same duration, you get different magnitude. So when we sample more than 3 or 5, we get to see similar things depending on the motion, but it was already promising. So then the question arises, so this is only one text, like usually there's just one jumping, but we want to generate long sequences, infinitely many, and this transformer that we've designed, it's like takes the whole thing at the same time, so it's quadratic complexity if we want to have long sequences. And the idea is to modify, well, to build on the previous work to make it handle the sequence of text. So that's kind of similar to what I showed before. An example for inputs: wave the right hand, kick with the left foot, catch an object, throw an object, lunges forward, stand, sit down, turn left, and sit. There's no way you collect such data annotation, but this is at test time. We can just add some demo. But what you get is, at least, like recently, people have started annotating large motion capture data like AMAS into sequence of things. At least it's common to have one after the other, like two pairs of motion. So given that, we can modify, remember this TEMOS, which was the text and motion branch. We can just modify the encoder, the text encoder, such that it's aware of the past. So we generate auto-regressively at the action level, but non-auto-regressively within the action. So we generate at the very first frame, there's no past, so we just generate text to motion. And then for the next one, we make it aware of the previous frames so that it generates something smooth. In practice, there is still a gap that we bridge with some slurp, some interpolation, but that gap is much smaller than if you just generate randomly independently. So that was like idea that was simple, but we showed like lots of use cases, and I'll skip that. If you have questions, we can talk about it. But towards this more fine-grained description for an existing motion, so having multiple text that describes the same motion, we thought of separating things that control different body parts. So I can be waving while sitting. So my sitting is relevant to my legs, waving is relevant to my arms. So like trying to associate actions to part of the text. So we looked at simultaneous action generation. I'll skip that maybe. So that we could have put hands on the waist with different movement of the torso at the same time. And traditionally, or well, even now, if an animator wants to do that, let's say you want to do two things, you would, if you have a motion of this raising arms, you could annotate, okay, the arms are involved with this action, and I want to combine it with the sitting motion. I annotate the legs. I can just stitch them together. Of course, there's like some edge cases, but you can have something that's reasonable. And the idea here was that this manual typing of body parts relevance can be done with a language model. They know really well what is involved in what. So we asked like, what parts of the body are moving when someone is doing the action X? Squat down, like we just gave it all the annotation, possible annotations in terms of actions. Of course, in practice, the prompt was a little more structured. We gave them, these are the body parts, here are some examples. To make it easier to parse, so that if we have two annotations, raise arms and stroll with corresponding motion, we could just synthetically composite them. This can be a baseline of method on its own, but we used it to generate synthetic data so that we could train on them later, because there's no way you get such fine-grained annotation for composite actions. Okay. Otherwise, the model is the same. We just concatenate things like during, while, simultaneously, and at the same time. But for us, the input is really like more like a set. And it worked pretty okay for such a complicated task. So move left leg in circles while spinning backwards and so on. Sit down, drink, answer phone, sit down, kneel down, tie shoelace. All right. But we have kind of tackled each problem separately, independently, for the temporal composition one after the other versus the spatial composition at the same time, or the single text, which was the basis of all these models. But as I showed at the beginning, we want something that can do all of this at the same time. So that was the multi-track timeline, an interface that changes for the user, but also the method development. So I'll just first show this example. For defining the task, so walking in a circle until this moment, start waving the right hand, stop moving, start jumping. So if you really want to put it into a single sentence, it would get really complicated. But this way you break it down. Well, method-wise, we've switched, well, partially because the student wanted to work on diffusion. Partially, this was kind of a natural and easier way to combine multiple motions together. So I'm not going to go into detail, but what we really need is a model, a diffusion model that goes from text to motion. It's trained on single text, single motion data. And at test time, we use that. Let's say we have 3 inputs to simplify things. We would independently start denoising text plus a noise with that model. And at each denoising iteration, you would do some kind of arithmetics, especially identifying the transitions to make them communicate. So you just like, let's say, take half of the values from the noise 1 and the noise 2 at the corresponding frames, and then add them together, give them back to their independent denoising step. For the body parts, though, we go back to GPT or like some language model to ask which body parts are involved in this action versus that action. So we slice the noise vector and then sum them together and like denoise. So there's like, this is based on Diff Collage, this work that did that for image stitching, based on a pre-trained model that has never seen compositional data. So you don't need to train anything. So it's just a test time denoising method that in the end was working pretty well. Example, go forward, raise hands. But you might say, okay, the jump didn't really start there, it started here. This is because of the data where you have seen jumping usually starting from neutral motion and then jumping. There's always some of the motions, they have this lag. So you would maybe need to identify these things a bit better. Okay, so you've seen at the beginning some teaser, but as I said, sometimes the motions that are generated are not as good quality as the real ones. So physically, maybe there's foot sliding, or you know that you had that motion already in your database. So why not just treat that? So that's why we did this text to motion retrieval TMR work. And the idea is super simple. So you want to train something like CLIP, contrastive learning, for pulling the positive pairs between text and motion together. So the diagonal should be maximized and the off diagonal should be minimized. So that's like info NC loss. Super simple idea. Except that we've already done that a little bit with the TEMOS work. So the text motion branch and motion to motion branch. In that work, remember, we had a loss to make the text and motion embedding similar to each other. The main difference here is that we see negatives. So there it was just seeing positive pairs. Now we incorporate a batch and then make push the things that are not supposed to be matched far away in the embedding space. And even if we do it for retrieval, we have shown some benefits of keeping the motion decoder. And that's, I think, because of this shortcut I was mentioning. So if you only seen I don't know, a left kick with waving hands in the batch, maybe you don't even encode left anymore. It's enough to just encode kick. So you can discard some of the words, but if you need to generate it, then you have to pay attention to all the words. So this is the same idea as like blip and image text retrieval. They also have a captioning loss to make it pay attention to all the words. And one tiny thing we had to do, which made a big difference, was this filtering of negatives, meaning we discard some of the negatives from the loss. And that's a bit specific to human motion databases because it's all about humans. So the word human is in every sentence, but also there are different ways to describe the same motion. And it's like a lot of walking in this database, and even things like turning counterclockwise versus quarter circle to the left. Like they can be, they don't have to be, coming from the similar motion. So we discard those and get some boost. But this is kind of a summary of some of the performance boost was from, so that was the only work which was doing that before for another purpose, but using max margin loss, just triplet loss, versus N4 NCE using the entire batch for the negatives. So that gives a big boost. TEMOS meaning just having positives versus using negatives, that gives underwhelming boost. But having the motion decoding branch, so having both the contrastive loss and the generation reconstruction loss, that was the best. And you can play with, so there's a demo online where you can type some text, like a person begins to walk. And you would find these motions that look, I mean, they're all begin to walk upstairs. Oops. Too many examples. Yeah, so for example, pitching a ball, there's a lot of them in the, well, These are all made for like some fancy submat videos that are supposed to play on their own. I'll try not to touch. Okay, so these are all pitching the ball, but the actual exact sentence, which was supposed to be the ground truth, is only at the rank 10. That's why also evaluation of these are a little bit tricky. So all these 10, they could be positives as well. So we look at some semantic similarity between, like text-to-text similarity between motions to determine which ones are potentially false negatives. And one nice thing, it's my favorite part of this paper, is using this model, which was not built for moment retrieval, make it work for moment retrieval. So what I mean by moment retrieval, so I have this video, well, the motion, and I want to identify the moment it's done doing backflip. And this is very simple sliding window motion text similarity 1D plot. And we can say that if it's above some threshold or if the peak of the signal can be the localization. And we're calling it zero shot because we have a database at the time that came out, Babel, that was annotated in a long sequence with short segments. So we could even evaluate these subtle movements like pivoting 180 degree. It will color up for the ground truth and the prediction, but it's very obvious in the signal. And if you really want to go a bit deeper and do counting, how many times I'm doing, I don't know, tossing object or with right arm, there are some repetitive ones. Well, jumping jack, I think. Like some of the things that are repetitive, you can do counting even like very easily by looking at the signal. But, well, there were lots of problems. In the follow-up work, we've noticed that more and more data sets are coming out, like Babel, KIT, Human, and ML3D. They are all like the same motion capture data annotated by different people. And they just have different style. Some of them say punch. The other one says and make a fist and then move your arm. So in the text embedding space, when we visualize the TSNE, we just saw a clear distinction between the Babel dataset that has this very short action-like text versus the full sentences that already almost describe the same motion. What we do is simply some text augmentation to make the short ones expand and the long ones shrink, basically by telling language model and giving examples again. And that improved the zero-shot training on the verbose data and zero-shot testing on the short data. It improved quite a lot if you augment this. Any questions? My last and quite excited part of my talk is this editing. So I have a source motion. I've either generated it or somebody gave it to me from existing motion. And I want to type some text to modify it, kick higher. We've seen this example. It's easier to see when they're overlaid, so the difference. So we have got used to seeing this when looking at qualitative results, for example. And when you look at the state of the art or even the literature, there's nothing that is designed for this task. There are models designed for text to motion where they can say, okay, mask lower body part manually and give another text to modify it. So you would need to know which body parts to mask. So that will be done manually. So this is motion diffusion model that has shown some applications of it for editing, but is not meant for editing. And it's trained only for text to motion. There is more recent work, which is actually quite interesting, on SIGGRAPH that uses a language model to generate code, given some rule-based stuff that say, if it says as you jump, then you need to like make it throughout all the time frames. If it says at the beginning, you need to do it all. So it identifies frames and then modifies those frames given some rules and joint rotations. It's quite complicated, but it works for certain edit types quite well, but not for generic open free-form text. What we've done in this work is to collect data for this in the form of triplets. So you need source, target, and edit. So it's difficult to collect that. And how we've done was the main question here, which took a lot of time. in 2 steps in a semi-automatic way. The first step is we have already this text motion retrieval model. We have some motion encoder, forget about text. We have some motion encoder that has this fixed size vector that can do similarity between 2 motions easily. And if they are similar in space, we have this hypothesis that 2 motions that are similar and not exactly the same, they might be edit distance apart from each other, that can have a meaningful text that can be typed. So what we've done is give these pairs of motions to mechanical Turkers and tell them, describe and edit between 3 and 12 words, otherwise it was getting out of control. And if it's really getting out of control, that means they are too different to make a meaningful edit. So then they can skip, they are too different. Or if they're really the same, they can skip and say they're too similar. So with that, we've collected in a relatively short time, I don't remember exactly, but a couple months, 6,700 triplets. And this is to give you an idea at the same scale of data, which was recently also collected for pose editing, so static poses, and smaller than only text to motion, which is you just give it motion and make them type text, which has been done concurrently with these 2 works, and that's on the order of 10,000, 15,000. So it's still very small, but enough to train a model. So I'll just show some dataset examples for the word higher. So you can do throw at higher angle, reach higher with arms. So it's the same word in different contexts can mean different things. Put your hand higher on the head. Or you can have these, don't bend down from the back, instead bend sideways. It's change, like it has these words like instead, so to refer back to the source motion. Do it faster, catch from higher. Or do 1 more repetition. So if you're doing jumping jacks. So it's not easy to encapsulate all this into a single rule-based method. So that's why the data-based approach was turned out to be the best. And you can there's an interface on the project page. You can just browse the data to see it. And in terms of the method, the denoiser, well, like diffusion models are a little bit natural way to deal with editing, because you start with a motion and you modify it. So it's like you give the source motion as one of the inputs, you give some noise during test time and the actual target during training time, the noise version. And there's the text condition, which is encoded with some text encoder, and the timestamp to know which diffusion timestamp you're in. And then you trained it fully supervised with our data. I'll just show 1 example or 2 for the results and without numbers. But just to show the turn back sooner while crawling, on the left is our prediction, the green one. I don't know if you can see. It's correct, but it's not the same as the ground truth. Sorry, it's the other way around. This is the generated, it's correct, but it's not the same if you just do some distance-based metric. It's not easy, so evaluation is tricky here. Maybe 1 more. Don't move the upright hands left and right, just keep them straight. The blue one keeps them straight. It's a bit awkward. But with all that, to say that these are all like new tasks, most of them introduce like slightly different version of this language and motion related tasks, but there is a lot to be done. This is just the beginning of it, especially on the data side. A few thousand is nothing these days in generative models. Like we're training image models with millions, billions. So how to get that data going outside Motion Capture Studio? Obviously videos, but how do you actually get in the wild videos with captions working? But people are starting to look at that direction. Another direction which is coming up is a more object conditioned, scene conditioned, multi-person. So given the other person's motion, what is my motion? So it's interaction generation. Well, evaluation is a whole mess, but that's, I think, on its own a research problem. But yeah, where I wanted to come also, the discussion we had earlier is there are still things that are not describable by words, especially with the editing work, we've seen the limits of what can be described. People are like typing super complicated things. It's moving in front, but moving in which direction, or which, like circular motion versus linear motion, or along which direction. So this 3D is a little bit difficult to describe at the nuances. So in that sense, if you really want to give feedback to someone, maybe just showing a video or the image is much more effective than describing in language. And yeah, one last thing we're recently working on and things are getting promising is hand motion. So I'm also working on sign language, as I said, so describing to a learner how to sign some sign. That's, yeah, like you can put your thumb together with your index and start making a circular motion. So these are some of the things that I think will be the near future work. That I can take questions and thank the students, Mathis, Nikos, and new student Leor, who's done most of the work. Thank you.